Okay, welcome to the class meeting 16 of the spectrally correlated random processes. So we've done our second take-home exam, and I believe that clarified a lot of your questions related to the previous paper, asymptotic frequency shift properizer for block processing of improper complex second-order cyclostationary random processes. So as I promised you, we are going to cover the harmonic series representation and other papers. Before doing that, I found I need to bridge the harmonic series representation and translation series representation by providing you some knowledges not appearing in these papers. So the first thing is so-called shift invariant subspace and its generators. So I generated this PDF using Gemini. First, I asked several questions by providing some side informations, which leads to my desired result, and asked it to convert it to LaTeX file. And then I used Text Studio, and it was almost instant to generate this page. Of course, I believe it hallucinated a lot, so I'm not sure which part is correct and which part is not correct. But anyway, it's a good start point, so I'm going to talk about it. By the way, today's class meeting is very much motivated by the class meeting 24 of 2018 course. So if you go to EC 695M schedule, then you will find 2018's schedule and download table. And if you go to class meeting 24, then you will see one PDF and one YouTube link. So this is PDF and this is YouTube. Unfortunately, the class meeting at that time was recorded in Korean. So you may just use this PDF file almost written in English. And if you are Korean, then you can access this YouTube video to be helped. And today's version is in English, and I'll do my best to clarify these ideas. Okay. So let me see. Just a second. Why this appears first? Okay. One page is missing. Just a second. Why there is periodic? Oh, okay. MS periodicity. Okay, got it. So let me talk about the mean square periodicity and Y-sense periodicity and their relation to Y-sense cyclostationarity. You already know a lot about Y-sense cyclostationarity. That was one of the main topics of this course. So let me, at the first, confuse you a lot by introducing these two new concepts. So you must be alert, very much alert, and try to find out what's the difference. The first thing is the definition of a periodic signal, of course, before we talk about some periodic random process. So let's focus on continuous time signal, x of t, which is periodic. If this definition is related to the existence of something, there exists t positive such that x of t equals x of t plus capital T for t in real. Okay, so you need to find a positive real number capital T in order to show a continuous time signal x of t is periodic. Of course, here T is called a period of x of t. So simply put, x of t is periodic with period capital T, a positive real number. Ready? And as you see from here, if you visualize what's going on is that if you choose any real number t0, then from this t0, you evaluate function x, and this value must be same as the function value at t0 plus capital T. And also, if you repeat this one by redefining t0 as t0, or just consider this as t0 plus capital T as t1, then what will happen? t1 plus capital T, which is t0 plus 2 capital T, you have the same value, and so on, which means that actually x of t0 equals x of t0 plus kt for all k integer, right? Not only at 0, if k equals 0, then x of t0 is always x of t0. So this holds. And this equality also holds for all t0 in R. So in many textbooks and papers, periodicity is defined this way. xt equals x of t plus kt for all k integer for all t real, and there exists t positive. Got it? And the difference is not that significant at this point. So here in the original definition, we only said x of t equals x of t plus capital T. So there is no k here, right? If you really love simplicity in any definition, probably you love this one. That's why this definition appears in many of mathematics books and signals and systems books. Got it? But they are actually the same. Got it? Both of the definitions rely on the existence of a positive number, capital T. There are tons of related chats I need to add, something like that. Okay, so here goes the trick question. So if T is period, then KT is period. Is it true? So if T is a period of the periodic signal, then K times T and K integer is also period. Is it true or not? This is just teasing question because as I just told you, right? What will happen? This holds for all T, right? However, the answer is no, because we define a period as a as a positive number. So that is the trick. So if k is limited to an integer, it's okay. But it's like you can never say that, okay, 5 is period, so -5 is period. We don't say that. Got it? So that is very certain. In many cases, professors in teaching electrical engineering signal systems, that they don't talk about it. But this is required because we are going to define one thing more. So here goes the definition. The fundamental period of a periodic signal is defined as the smallest period of the signal. So if you just allow negative number as a period, then we never have fundamental period in this way defined. We probably need to take the absolute value. That's why people love period to be a positive number. And there goes another question. So question, the fundamental period always exists. So now we have limited our periods as positive numbers. And the question is, the smallest one, the fundamental period, always exists or not? And as you learned in signal-gen systems, especially in Fourier series, probably you remember those direct delta functions appearing in the frequency domain after Fourier transforming the periodic signal. Unfortunately, the answer is no again. There are two examples for this answer no. And still, this is just a teasing problem. Practically, it does not mean much, but let me give you an example. The first one is that you have some constant function. And the question is this constant function a periodic function? Yes, right? Because this is constant, so what do we have? We have, for all positive real number t, we have the equation well satisfied. What does that mean? Any positive real number can be a period of a constant function. And every positive real number set does not have the minimum, the smallest one. So this function does not have a period, even though it has uncountably infinite number of periods. So it's just a teasing problem, okay? So no fundamental period. The reason why this problem is not that important is that we electrical engineers usually think in the frequency domain whenever we confront a periodic signal. And we just have an automatic spectrum analyzer. And we seek direct delta functions. And if you have a constant function, you have direct delta function located at f equals 0. And you may say that, well, where are the harmonics, something like that? What is the fundamental frequency? Got it? So it's not that important, actually. And by the way, a companion definition is the fundamental frequency. That is defined as the inverse of the fundamental period, assuming its existence. Got it? And another one is that tricky one appearing again and again in every analysis problem. So it's like it is 0 for all Q, 1 for all irrationals, something like this. So probably when you studied the difference between a Riemann integral and Lebesgue integral, probably you've seen the function like this. So usually the function was limited to 0 to 1. And what happens? For every rational number, the value is 0. Every irrational number, the value is 1. Now we have extended this function to the entire real domain. Now, let me ask you a question. What happens if you choose some t0 and t, both are rationals? What will happen? So rational plus rational is rational, right? So this number, x of rational, is 0, right? And that is same as xt0. right? So x of t0, a rational t0, is periodic just for rationals, for any rational number. And also, you have the same thing. Be careful here. We choose rational number t. Then what happens? Irrational, x of irrational is 1, and x of irrational plus rational is x of irrational. That is also 1. Am I right? Or wrong? Yeah, probably I'm wrong. Probably I should switch it this too. Just a second. Just a second. Just a second. Yeah, something's not correct. Just a second. Am I right? Rational, irrational, rational, irrational. Yeah, I believe I'm correct. So here again, this x of t has t positive and t rational. Okay, so let me just write this way. As a period. Am I right? So every positive rational number is a period of this signal. Probably I'm right. Yeah. So this periodic signal still does not have a fundamental period because no minimum value over positive rational numbers exist, right? But these two signals are a little bit, how do you say that? Pathological, okay? As a periodic signal. By the way, this terminology is not a well-defined mathematical terminology. However, if you read math books related to functional analysis, especially harmonic analysis, this word appears quite often. And even though it's not well defined, they want to remove these such strange functions, like taking 0 in rational, taking 1 in irrational, something like that. Usually, we love what kind of functions? Riemann integrable functions. Whenever engineering students and researchers handle or model the real-world signals. Okay, so except the very small number of pathological signals and functions, if you just consider the spectrum of the signal, then what happens? You may have some Dirac delta at 0, which is related to the DC term, constant term. And usually you observe delta functions. And if delta functions are equally spaced, then what happens? You may consider a harmonic series. Okay? Of course, harmonic series in the sequence usually means what? Something like this, right? This is harmonic series in most of the cases. However, in Fourier analysis related thing, as if we have power series and Taylor series representation, we may define harmonic series and Fourier series representation. What's the difference between power series and Fourier series representation? Power series means that your function is defined in the form of a power series, summation of constant times x to the n, something like that. So you start, from the start, you define something like this. Sorry, power series. Power series. Got it? Of course, finite order. Otherwise, it does not make sense. So in harmonic series, you have something like this. And usually, when you talk about harmonic series, we allow infinite terms. So you may just say, even in power series, we may just allow countably infinite terms. And here, countably infinite terms. Of course, here, we have, especially here, a real valued power series. And what is Taylor series representation and also power series representation? In this case, x of t is given. And you want to find representation, an alternative form of x of t that equates somehow with this power series. Got it? So representation means that you already have your function and you want to rewrite it in the form of power series. Same happens here. Suppose you have a periodic signal and you want to find a new form, new alternative form in this way. That is Fourier series representation. Got it? So be careful. So here, whenever you see something like this in the spectrum analyzer, probably you want to do something like this, taking F0 as the inverse of 1 over T0. Got it? So whenever you see this one, you say that, hey, F0 is the fundamental period, a frequency, and its inverse is fundamental period. Got it? If you start from the frequency domain. And that makes sense because here, if you replace T with T plus capital T0, then the equality holds for all T. Got it? So definitely you have a periodic signal. Of course, you may view this in a strangely different way. So as you've seen just, a periodic signal with period T0 is also periodic with period any integer multiple of T0. So let's think about 2T0. And your new period is lengthened, which means that if you view this one as your period, right, what is the inverse of it? So it's lengthened, it is halved, right? So now you are looking at this frequency and your new period does not generate any new frequency component. What's wrong with it? Here, we may have some delta functions in every half frequency spacing. And that is just because what? Your every other coefficient is 0. Got it? So the signal is just there, and you change your point of view. In that case, your signal may have what? May have a smaller fundamental frequency. And usually, in this case, we don't call this a fundamental frequency because that is not the smallest one, right? So it's like we may view the signal as a periodic signal with longer period. However, our fundamental frequency and fundamental period does not change. Got it? So if fundamental period or fundamental frequency exists, then it's unique. And we defined them to be unique if they exist. Got it? So changing the point of view may confuse us, but that fundamental is still fundamental. Got it? Anyway, so far we've seen periodic signal, and now we want to extend this notion of periodicity to random processes. What will be the extension? So we start from a continuous time random process x of t is, what do you want to define? A random process is periodic? What would that mean? A random process is periodic. What would that mean? Just a deterministic signal? What do you guess? But here, we first define mean square periodicity. And after we review that, let's go back to the original question. Ready? So a continuous time random process x t is mean square periodic if now we have periodicity, but mean square periodicity. And mean means ensemble average, right? And square periodic. What does that mean? What is squared? So we go back to our definition of periodicity and find an alternative form. What would be that? So take a look at this one. Whenever you have A equals B, actually that is equivalent to A minus B equals 0. Am I right? So this means right? Now, whenever we have mean square something, we usually have what? Mean square something equals 0 or converges to 0. So now, what if we take this left-hand side and change x of t as the capital X of t? And then what? Still just, now, another one is this one. What if we take the square of it? Something squared equals 0 if and only if something is 0, whether something is real or complex value, right? So this is okay for the definition of periodic signal, although it's very not simple. If we want really simple, compact form of definition, no one would define a periodic signal in this way. However, if we want to generalize periodicity over deterministic signal to a random process, we may need this some strange, cumbersome, totally, completely equivalent representations of the definition, right? So here comes the definition of mean square periodic random process. Got it? So here you have mean, right? Now you have square. And what? This is very similar to periodicity. Got it? So this is the definition of mean square periodicity. And let me ask you a question. So at some t0, if you evaluate the random process x, then you have a random variable, right? So here, if you just not considering every t, but just one single t0, and you plug in What does that mean? You have expectation of x t0 minus x t0 plus t. So you may view this as some x and this as some y. So my question is simply, if this holds, are x and y are equal almost surely? So here you have to know the definition of almost sure equality of two random variables. And what does that mean actually? Almost sure means that probability of event that these two random variables are equal is 1, right? So with probability 1. And if you just extend the idea that a random variable is simply a random process is simply random variables at every sampling instant, is that you are sure about this one. So this holds actually. So it's like at t0, you have some random variable, xt0. And at t0 plus t, you have another random variable and another random variable. What happens? This means verbally, these two are what? Almost surely equal. They are, right? And these two are almost surely equal. And by using the triangle inequality, you can show that this and that is equal almost surely, right? So pairwise almost sure equality you have. And I'm sure that you can show that they are jointly equal, but that does not mean much. Yeah. Anyway, so far, so good. And you have another set of almost surely equal random variables by simply choosing different sampling instant. In this case, T1 other than T0. Got it? So you have almost surely equal random variables for mean square periodicity. Okay. Now, the question actually is not, is this related to the Weissen's cyclostationarity? The question is, find the property of a mean square periodic random process, especially what are the second order properties. So whenever we say second order properties of a random process, first, second, what do we need to evaluate? First, the mean path as a function of t, right? And we are going to denote it as mu sub x of t. Second, autocorrelation function. So if it is complex values, then we will have conjugation. So the question is, when x of t is mean square periodic, then what are the properties of the mean path and the autocorrelation function of this random process? And you can show that the mean path is periodic. And its autocorrelation function is periodic in T and periodic in S. Got it? That is written here, I believe. And there. Be careful. See that? Here, the Gemini says the autocorrelation function evaluated at T1 and T2 satisfies. You may replace T with T1 plus capital T, and you may replace T2 with T2 plus T. But actually, this is another version. If you use my term, this one. Because what? In between these two, you may have T1 plus 2T, right? Because of the periodicity. You may have T1 plus MT here. And from here, you may have T2 plus NT. So you have this same as that one. Got it? So we've seen what? If x of t is mean square periodic, then we have mean path periodic, and its autocorrelation function is periodic in T and S. And here comes the confusion. What was the definition of cyclostationary random process? So here goes the definition. A continuous time random process. Of course, we assume second order. Here, second order means that finite power is Y sense cyclostationary. Here, as you see, Y sense means what? Your definition is related to the first and second order moments of the random process. Got it? Oh, by the way, here I forgot another definition. I'm sorry. I need to define this term first. Here, definition. A continuous time random process x of t is Y sense periodic if 1 and 2 are satisfied. Got it? And here goes the lemma. Mean square periodicity implies Y sense periodicity. And converse in general is not true. Okay? So it's our researchers and professionals' convention that in the context of random process, when we say Y sense, we usually talk about mean and autocorrelation function. Got it? It's very unfortunate that people didn't consider complementary autocorrelation function. That's why sometimes in my research paper, I defined second order cyclostationarity in order to make the complementary autocorrelation function also periodic in T when we use the parameter T and T minus S or something like that. Right? Anyway, so let's review and compare these two definitions. A continuous random process x of t is Y sense cyclostationary if what? The first. The mean process is periodic. So the first condition is the same as the mean square periodicity. What is the second one? Second one is the property of autocorrelation function. But actually, we may prefer covariance functions. So you subtract the mean first. and take the conjugation. So for all t comma s, yeah, and there exists positive. So by the way, the second condition can be replaced by the autocorrelation property. Because if you expand this one, then you have the same result. Got it? Anyway, let's focus more on this 1 and 2. So what are the differences? The first one is exactly the same, right? Am I right? What is the difference in second one? If you just compare, you have freedom M and N. And here you may say M and M, okay? So for all t comma s and for all m, that is integer. Okay? So you don't have freedom. You have the same coefficient m. Here you may have different coefficients m and n. That makes huge difference. As we've done already, let's visualize and see the difference between Y-sense periodic process and Y-sense cyclostationary process. And if you remember, I have taken the square of size, height, and width t. And what happens? If you have some contour of the magnitude, for example, for the autocorrelation function like this, what happens? Then you move by capital T to the horizontal axis, along the horizontal and vertical axis. So you have something like this. What about here in Y-sense periodic case? If the contour has these level sets, then you have the same thing here. Now, what does this mean? You have to copy and paste this square to any right side shifting left and left side shifting, up shifting and down shifting. So your autocorrelation function is actually made of a single same tile. So for example, you go to a bathroom, especially in Korea, then usually your bottom is covered in tiles. Okay? I still remember I was shocked when I first went to the US and found there is no draining hole and the floor was almost same as my room. And there was a warning that for the Asians, especially Koreans, don't pour your water on the floor of the bathroom, something like that. Okay? Anyway, So this is a kind of level sets of the autocorrelation function of a Y-sense periodic random process. What about here? Probably you remember because you studied twice about the exams for the exams. So it's like you may have some different type, right? And you have the same tiles for these off-diagonal elements. If it's real, then you have kind of symmetrical tiles here, something like that. Got it? So which one is more general? Which one is a bigger set? So let's draw a Venn diagram. So here goes the set of all second order, which means finite power, continuous time random processes. Then we have very small set of mean square periodic random processes set. And then from the implication between mean square periodicity and Y-sense periodicity, Y-sense periodicity is a bigger set, right? So here goes Y-sense periodic random processes. And since this property implies that property, this second one implies that second one, we have Y-sense cyclostationarity here. Got it? So this is the relation among mean square periodicity and Y-sense periodicity and Y-sense cyclostationarity with period, for example, capital T, a positive real number. Got it? Am I done or not done? Let me see. Yeah, I believe I'm done with this one. Okay. Now, let's go to the second topic of today. And that's confusing more, unfortunately. So here we have a counterpart, the set of all continuous time signals, no randomness. Then probably you remember we started from a periodic signal, right? So here comes periodic signals. Got it? And it could correspond to that one. Okay. Okay, so let me just make it bigger and shade with the same style. And here goes the question. So we are going to extend this definition somehow to have some flavor like this Y-sense cyclostationarity. What can we do? That is the question. Got it? And that is related with shift invariant subspaces and the set of shift invariant signals. But there is unfortunately a different property with that one. That is the very problematic one. So anyway, let's take a look at next PDF file, again generated by Gemini. So the title is Shift Invariant Subspaces and Their Generators. And the notation is very unfriendly. So let me just give you an idea. Suppose you have some function phi. Now you shift it by some integer multiple of positive number t. Now you multiply some coefficient an and you generate the signal by summing up. Okay. Now suppose you have the set of all signals generated in this way. So you have a single function b, and you have chosen capital T. So you have two parameters, phi and capital T. Here phi is, of course, phi of t. So you choose these two, a function and a positive real number. And then, depending on realness or complexness, usually you choose some sequence, complex valued, and then you add them up. What's wrong with this definition? Convergence, okay? Because you have infinitely many terms if you have something like this. So people didn't want to have this trouble. Here goes why, what they did for some trick. So usually, not always, usually they have this constraint. So you have your discrete time in terms of electrical engineers terminologies. This discrete time signal A sub n, that is of finite energy. And usually we just say that A sub n sequence is what? An L square signal, an L square. And L is, I asked the Gemini and found L is from Lebesgue, who contributed a lot to the major theory. Anyway, so L2. So these means just L2, finite energy. In that case, if phi of t is also a finite energy signal, then you can show that x of t is of finite energy. And what's good with that? Fourier transform exists. Precisely speaking, Fourier Plancherel transform exists. So you can view this signal in the frequency domain if you want, and you think in that way and process there and go back to the time domain without much difficulty. Got it? Now, let me ask you again. Suppose you have x of t that is generated by phi and sequence, finite and sequence an, this way. Now, if you shift x by capital T, is it also in this set? Of course, right? So from a finite energy signal and positive number T and an L2 sequence, right? By choosing any L2 sequence, you can define a set. Parameterized by phi of t and t. By the way, inside this one, you may have different sequences, not just the shifted. Ready? And if you choose a signal here, by definition, any translation of the signal by integer multiple of t is still inside the cell. Got it? And another one is this one. So what if we choose more functions than one to construct the signal x of t? By the way, here phi is called a generator. Or a generating function. So the question is, what if we choose more than one generating functions? Actually, we can do that. So we may choose phi1 and phi2, both assumed finite energy, and choose a single parameter t. And we may construct the signal in this way. So here, m is related to the amount of shift of phi1, and n is related to the amount shift of phi2. Of course, you have many, many, many other cases. Yeah, just a second. Something's not correct. What is why? Just a second. Just a second. Something's not correct. Am I correct? Generate. Rate is some. Yeah, something's not correct. Just a second. Just a second. Is it true? This is what I do not. What this is not what I remember. Okay. Ah, okay. I got what. Yeah. What's wrong with it? Mm. Yeah. Okay. Got it. Sorry about that. Delete what I told you. Not this one. This is something different. Sorry about that. Am I right? Yeah. N. Yeah. Yeah. Still something's not correct. Just a second. Yeah, man. Yeah. See? Yeah, it's correct. So here m is either 0 or 1, not everything. 1 or 2, sorry, 1 or 2. So actually, you have You can rewrite it this way. Got it? So very similar to the summation of two QAM signals. Got it? And you may generalize this one. So you have B1 of t, B2 of t, dot, 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 Bm of t, and capital T. So X of t is simply sigma, and you have B1 and B1 t minus nt plus B2 and B2 t minus nt dot dot dot. You have B sub capital M of n, B sub capital M and t. Now we use double summation. Bm n Bm t minus nt. So if you define this as Bmn, then we go back to what I wanted to tell you. Bm t minus nt. Got it? So do you see some parallelism between this shift invariant signals and linearly modulated signals? That becomes, in many cases, Wise-and cyclostationary random processes. Of course, if you remember properly, then QAM signal with data modeled as a Wise-and stationary random process give you Wise-and cyclostationary continuous time signal. You remember? You must be careful. Got it? So you may have some other set of signals now generated by phi that consists of generator functions and something like that. Usually we assume that this B sub 1 sequence, B sub 2 sequence, B sub M sequences are all finite energy signals, which implies that BMN, this two-dimensional signal, is also a finite energy signal, two-dimensional signal. Got it? So inside this set, given these two parameters, you may just use Fourier Plancherel transform, which is very good for your frequency domain analysis. By the way, this shift invariant subspace is because of this one. So just consider some, how do you say that? Just consider the Hilbert space of band-limited finite energy signals. So let's assume that we have the set of finite energy signals and band limited to, for example, plus minus W over 2, so complex value. Then what is this set? Is this set has some interesting property? And the answer is yes, actually. And this set is very similar to a finite dimensional Euclidean space. Why? Probably you remember these two conditions appeared already when you studied the sampling theorem. What does that mean? If you have this set, any signal in this set can be sampled using a uniform sampler at the rate of twice this bandwidth, so W, to fully preserve the information in the signal, and also the sampled output sequence, discrete time sequence, contains all the information to fully recover this signal, right? What does that mean? Actually, if x of t is in this set, let's say this set as some set H, okay? If a signal, a finite energy band limited signal is in this set, then what happens? This signal so you consider countably infinite number of correlators, which actually projects this continuous time signal to the direction of each sync pulse with uniform delay. Got it? Now, with this countably infinite number of branches, you can obtain the discrete time sequence x of n. And what do we have? The left side, the original signal, is same as the series in the mean square sense. The convergence is in the mean square sense. And what's the difference between these shift invariant signals? Now suppose you have this generator is all band limited. So phi of t, phi sub m of t is, as we assumed already, of finite energy and also band limited to W over 2. Then what's the difference between these two? In general, this set is what? Forms a subspace of the entire space of this H. Okay? So you may regard H as, for example, C to the n, some large n. And what happens? Here, this set can be viewed as a subspace with m dimension if phi sub m's satisfy some condition. Some some non-linear, how to say it, they do not, how to say it, they are linearly independent signals, something like that, okay? Linear independence, and if M is less than N, then this subset forms a subspace in general. If M is larger than N, and then they may fully span the entire subspace. Got it? That's why this name shift invariant subspace is coming from. So in general, they do not span the entire space. That's why this SIS appears. So we have around 3 minutes, and let me clarify what you already know. So here on the right-hand side, we have random processes, and left-hand side, we have deterministic signals. When we handle random processes, we always or almost always want second-order random processes, which means finite power random processes. What could be the counterpart when we handle deterministic signals? Finite energy signals. Got it? And about the bandwidth, we may or may not have strict sense band limitation, but for the derivation of some signal processing or communication or information theoretic results, we commonly use band limitedness of the deterministic signals or a random process. Got it? And here comes Y-sense cyclostationarity that is related to the mean processes property. And the autocorrelation property. Then what is here? Shift invariant subspaces generated by B and capital T. The reason why I didn't just write this is required is that the theory itself does not require this one. Okay? However, as I told you, to derive some information theoretic, especially information theoretic result, we need strict sense band limitation. And also in some signal processing point of view, we need that restriction. And you will see when we cover the idea of generalized Nyquist criterion, not today, on this Wednesday, okay? So you have now this idea, okay? Of course, here I just skipped here mean square periodicity or Y-sense periodicity, and here periodic signals. But as I told you, when you talk about finite energy something, these are totally unrelated, actually, ideas. Even though you may connect the similarity between Y-sense periodicity and Y-sense cyclostationarity. Got it? So be careful. Sometimes these parallelism make sense. Sometimes these are related, but this is not usually related. Otherwise, we have very complicated trouble whenever we see convergence issues here. Okay. Anyway, we covered up to that one. And let me just give you the preview. So here, you know the Nyquist criterion, not for the sampling theorem, but for the zero inter-symbol interference. And probably you started from the signal like this. And you ended up somehow some condition like this. Right? This is your so-called Nyquist criterion and Nyquist zero inter-symbol interference condition in the frequency domain, right? Now, the question is actually this one. What if we restrict this B sub n not to the, for example, BPSK signal or QPSK signal or something, but just we assume that this is a finite energy signal. Any finite energy signal. So this x of t is now in the shift invariant subspace generated by p of t and period capital T. What is your answer? So before we think about this problem, this Nyquist criterion, only in the context of what? Only in the context of inter-symbol interference, free transmission, right? Now my question is, what if we slightly extend or modify this one? So B of n is not just BPSK or QPSK data symbol, but any, in this case, real or complex sequence of finite energy. In that case, we can just think about this modulated signal as what? A kind of one of, not modulated, but this signal as an element of shift invariant subspace generated by P and capital T. Now the question is, still do we have some formula like this making sense or meaningful? If it is so, what would be the extension for the multiple generator functions? Got it? And okay, so can you do something like that? And also, we may restrict this one to some digital modulations constellation, or we may just generalize that one to a finite energy two-dimensional signal. Okay, that is actually the topic of this Wednesday. And you've seen this first one and quite familiar with that. And actually, I'm going to show that this is nothing but this formula using the vectorized Fourier transform of P. And this one, currently not clear would look like this one. Let me use P instead of phi. Okay, sorry about that. Got it? So do you see the parallelism? So if you can write the well-known Nyquist criterion in this form of inner product, then yeah, just a second. Sorry about that. This is not outer product. This is inner product. Okay. Then the first diagonal element is actually the same as this one for P1. Second diagonal element is for P2. Both diagonal elements, P1 Hermitian P2, 0. It's a kind of orthogonality. Got it? So this should be capital M. So size M identity matrix. Got it? Of course, if we have strict band limitedness, then we may have finite length signals, and we will have only what? Anyway, in any way, F is the Nyquist zone we have. Got it? So in this way, you may understand the well-known Nyquist criterion, not as in the form of summation of some continuous function, but in the in terms of the inner product over vector, and also Gramian matrix that gives you scale identity matrix, something like that. Anyway, that's all for today.